Hello? Hello, please respond here. Can you hear me? Hello? Can you hear me? Students, please respond here. Hello? Can you hear me? Okay, students, listen carefully here. Now, once again, good afternoon to everybody. Now, this is the yesterday one problem is here. Please note down. Now, through this meeting ID and password, please, you must follow the behalf of this session onwards. Please note down the meeting ID 8640973341. Please. Now, this is also one chart is here. Just you have to see, remember here. Meeting ID 8640973341. Password 98282878. This is for you. Must watch through this and join with us. Hello, students. Please respond here.
Yes,
Hello?
sir. Inpistunandi.
Okay, it's all right. Once again, sorry the trouble. Now, this is the university problem. That's not mine. Yesterday already first class is completed. Now, this is the second class. Okay. Now, then the continue of this part of linear spaces. Now, that is the linear span. Okay. Please stay on the line. Just you have to watch on the screen. Now, see, just you have to see and watch here. Look at on the screen here. Are you visible? Please respond.
Okay, sir.
Okay,
sir.
it's all right. Okay. Now, sorry the inconvenience. Okay. Now, then the continue of this part, linear span. What is the linear span? Okay. Now, let V be any one of the vector space. Now, that is the vector space over a field capital F. Now, that is the structure of a vector space over our linear space. Now, that is V of F under vector addition plus comma under scalar multiplication dot. Now, that is the structure of a linear space is V of F under addition under multiplication. That is the structure. Already later, yesterday class, we have discussed the difference between the basic algebra, group and ring. What is the difference between the group and ring? Now, both definitions are we have learned in, that is the fourth semester algebraic paper. Now, in that, just have watched and referred to have practiced some other concepts of modern algebra, that is the group and ring. Both are connectivity part. Now, group it satisfies only one binary operation. Listen carefully. Group it satisfies only one binary operation, and ring at the same time both operations are satisfied. Now, that is in the modern algebra, when the binary operations are ordinary operations. Now, just like that, ordinary operations are addition, subtraction, multiplication, and division. Here, the additive inverse is subtraction and multiplication, multiplicative inverse is division. Now, that is the normal operations, means are ordinary operations. Especially in this linear space part, means in the linear algebraic part, here the operations denoted as treated as addition, means that is the vector under addition, and multiplication means a scalar multiplication. Okay, already you have discussed in the previous class the definition of a vector space and some other examples. Okay, now just you have to see this one. At the same time, vector subspace is also there. Suppose group must follows the subgroup, and ring also it follows that subring of this part. Okay, in the same manner, in the linear algebra, total linear algebra, we must discuss throughout the dimensions. Dimensions means x-axis, y-axis, and z-axis. Okay, now let us see here, see this definition 1.3.9. Okay, that the definition is linear span. What is the linear span? Okay, see here. Now, that is the structure of a here V be any one of the vector space over the field. Just suppose here capital S be any non-empty subset of a vector space. Now, just you have to see, and you have to just visible here. S contained are equal to V. Now, sometimes it read as in the lower session, S is a subset or equal to V. Now, in the higher of this part, S is contained or equal to V, means S is a subset of V. Define here S be any non-empty subset of a vector space, then the linearity condition. Linearity means sum of the elements. Okay. Now, here AX, just you have to see here. AX means A be the field element. All the field elements are scalars. This is one of the important point. Student, listen carefully. A be any one of the scalar. All the AI values. I means it varies from 1 to n values. Okay. Now, AX means that is the scalar multiplication. Here, A being A is the element of field element. Now, that is the scalar. And X be any one of the vector. All the X elements are vectors. Now, AI, Xi values. So, that is A1 X1 plus A2 X. All the scalar, sum of the scalar elements. Now, that is called the linear span. Span means that is the generated element. Okay, all the subset of the elements must be is in vector space. So those vector space of the elements, we are taking the sum of the elements given in the subset, and according to the subset of the elements of a vectors to write as the sum, SUM sum, means overall the elements, that is the combination of scalar combinations. Okay, that is A1 X1. This is the one of the scalar multiplication. A2 X2. This is the another scalar multiplication, and so on An Xn. So sum of all the scalar elements, scalar multiplication of the elements to write as the sum of the scalar multiplications, to write as the linearity, to under the linearity part, to write as the linearity part, that is called a linear span. Okay. Now here n being the integer, that integer must be greater than 0 here, especially. Okay. Now here xi elements, we are taking the xi means here I varies from 1 to n values. That is the 1 to n representations. Okay. Now all the xi elements given in the subset and all the ai elements, here I varies from 1 to n. Now that is called the field elements. So this is the linear span is denoted by L of S. Listen carefully, students. Now this is one of the important concept, that is the linear span. Now through the linear span means that is called L of S. That is the representation of linear span is L of S. Okay. Now it follows the one of the theorem and one of the important property throughout the linear span. Okay. Here V be any one of the vector space over a field F. Now see this theorem. This theorem is also one of the important theorem in the final examination. Don't forget this one, because throughout the linear span definition, and to just have to remember this one. Enter these are all 5 conditions here. One is an equivalent to second one, and second one is also equivalent to third one, 3 to 4 and 4 to 5, and at the same time replacing 5 by 1 is there. because these are all one is an equivalent to say another one. Okay. Now that is the structure of a vector space. What is the structure? V of f under addition under multiplication. Now that is the vector space of the structure, means that is the identification purpose, because vector space is the first letter is capital V. So that's why we are that is all the alphabetical caps, all the alphabetical caps is denoted by capital V. So VB any vector space over a field capital F. Then for any S is a subset or equal to V, the linear span L of S is a subspace of V. Okay. Now S is contained or equal to V means this is one of the subset of a vector space, and according to the subset, non-empty subset of a vector space, we have defined the linear span. So that linear span is also a subspace. What is the subspace condition? Already we have discussed it in the previous class. What is the subspace condition? There are one is the one-step test, two-step test, and one-step test. Two-step test is alpha plus beta or x plus y belongs to W of f. So all that W of f, when the condition must be satisfied here. So any two vectors must be closed under vector addition, that is x plus y belongs to W of f. So that non-empty subset of a vector space is denoted by W of f. So W of f is contained or equal to V of f. All the subsets must be on given the set. Here the V of f is a vector space. So according to that vector space, we have to take in some of the elements given in the subset. Then according to that elements, we must satisfy the vector space conditions. So that's why that non-empty subset is a vector subspace. Now, one of the important subspace condition is, what is the subspace condition? Here x plus y belongs to W of f. Just you have to see and refer in the above theorem. Just see in your textbook. So yesterday we have practiced some other theorems. 1.3.1. This is the two-step test. X plus y belongs to W. W means W of f is contained or equal to V of f. And one of the scalar multiplication, Ax is also belongs to W of f contained or equal to V of f. This is your this is especially for your university material. And just you have to see and refer some other unified textbooks and regular textbooks. We are taking the elements is alpha plus beta belongs to W of f. The replacing xy by alpha and beta, whatever it is, no doubt. Okay. All the binary elements represented as the vectors. And some other elements A, B, C and so on. Some other elements are just like that. Here we are taking the A, B, C. Now those elements are scalars. Okay. Now here the representation of the unified textbook alpha plus beta, and that is the unified textbook means regular textbooks. Okay. Now this is the two-step test for subspace. X plus y belongs to W of f and Ax belongs to W of f. One-step test of subspace condition is Ax plus By belongs to W of f. So same binary operations must involved given in the subset of a vector space. Don't forget this one. Now this is one of the important theorem in the final examination. That is 1.3.7. This is one of the algebraic property for subspace. What is the algebraic property? Yesterday also we have discussed these properties. The intersection of any two subspaces is also a subspace. So W1, W2, there are two subspaces. Now that is W1 plus W2 are two subspaces. W1 intersection W2 is also a subspace. And at the same time, the number of subspaces we must assume the arbitrary intersection of the subspaces is also again a subspace. So that is represented as intersection of Wi or intersection of W alpha, whatever it is. Okay. Now that is the representation of just you have to see here. This is the arbitrary intersection of W plus alpha or Wi. Here I being the index set, here delta represented as the index set, means I varies from 1 to number of representations. W1 intersection, W2 intersection, W3 intersection, so on. So entire the part is called arbitrary intersection of the subspaces. Is also a subspace, means we must satisfy the condition of subspaces ax plus by. That is the one step test for subspace. One step test for subspace is ax plus by belongs to w of f. Now here the entire the arbitrary intersection means intersection of w alpha. Okay, now then the continuity of linear span is also, just you have to define the linear span L of S. That is the notion of, notion means identification of linear span is L of S equal to A1 x1. Sum of the scalar multiplications must be the addition, sum of means SUM sum. So overall the sum of overall the sum of, overall the means the sum of scalar multiplication is on linearity, that is called linear span. That is the representation of L of S equal to A1 x1 plus A2 x2 plus so on An xn. See this theorem 1.3.10, there is no doubt from the beginning of first and second unit thoroughly practiced, then automatically easy to get the pass. Okay, there is no doubt. That is the simplification, because without the concept of linear space, you can't do anything here. Okay. Now, here the property is S contained are equal to L of S. Just you have to see here. S contained are equal to L of S. S be any non-empty subset. That non-empty subset is also contained are equal to linear span. Second one, for any subspace W of V. For any subspace W of V means S contained are equal to W, L of S contained are equal to W. And third condition, L of S equal to S. Means S is a subspace of V. And fourth condition, L of S equal to L of S. Okay. Now that is the linear of linear span. Now this is also one of the remembering A dash whole dash equal to A. So that's why according to this one, linear of S equal to linear of S, that is also a vector space. And now the last one, last condition, S contained are equal to T. There are S and T, both are subsets of vector space. Now here one subset is contained are equal to second subset, and at the same time those linear spans are also, one is contained are equal to the other one. So L of S is contained are equal to L of T, because here S and T both are subsets of the vector space. Okay, next one. Now just you have to see and refer this, one of the proof is here. Okay, what is the proof? First one, to write as the linear span definition, L of S equal to A1 x1 plus A2 x plus so on An xn. Here n is greater than 0 and Ai means sum of the scalars. So Ai means I varies from 1 to n. Ai is the belongs to F, and here xi values are also taken given in the subset. By taking here the sum scalars, each and every one is 0. Each and every one 0. Ai equal to 0 means I varies from 1 to n. When the Ai equal to 0, we can observe that 0 be the at least one of the element given in the linear span. At least one of the element given in this L of S. So L of S is non-empty. Hence L of S is a, because 0 be the one of the element. That element represented is in L of S. So here the linear span must be the non-empty subset of V. So we are taking that at the same time, there are two elements given this one, here X and Y. See here, X and Y is there are two vectors belongs to L of S. Because to write as the X under the X values, one of the linear combination is an equivalent to one of the vector. X equal to A1 x1 plus so on An xn through the definition of linear span. And another element is, you are taking the one of the element is Y. Y is also in terms of Y values to write as the linear span B1 Y1 plus B2 Y2 plus so on Bm Ym. There are these here the scalars under the vector is X. Ai values are scalars given in this linear span, linear combination. L of S means A1 x1 plus A2 x plus so on An xn. Now the type of linearity is called linear combination. To write as the linear combination is an equivalent to one vector, that is the linear combination of the vector. and we are taking the another element given in the linear span, y be written as, y can be written as b1 y1 plus b2 y2 plus 1 bm by m. So ai values, bi values are the field elements, xi values and yi values are belongs to. Please note down here. Please just you have to rectify this one. Xi comma yi belongs to means is in. Belongs to means now sometimes it read as is consisting or is in, or in the lower session it read as belongs to. Okay. So here xi yi is also belongs to yes. So to write the x plus y. Okay. Now because here the subspace condition is x plus y belongs to w and ax belongs to w. So first of all, under the vector addition, to add the any two linear combination of the vectors x plus y, to write the x value plus y value. So just you have to write here a1 b1 of a1, so a1 x1 plus b1 y1, a2 x2 plus b2 y2, so on an xn plus bm ym. That is here now it treated as x plus y belongs to L of s. And at the same time scalar multiplication here. What is the scalar multiplication? Ax. X can also be written as what is the x? a1 x1, so on an xn. Enter that vector of the combination is multiplying with a. So a1 x1, aa2 x2, so on aan xn. So this is one of the scalar multiplication. So finally ax is also belongs to L of s. Okay. Now L of s is a subspace of V, because the L of s is a subspace of V. So first condition is okay. Now here when the condition must be, when both conditions are satisfied, because finally given the L of s is the subspace of V. Next, if x belongs to s, x can also be written as 1 into x. Okay. See this one. Here the condition, x being any one of the given the one of the element or any one of the vector given the subset, x can also be written as to write as identity element 1 into x. So this is also 1 being the field element. So this is also scalar multiplication holds given in the L of s. So that's why s contained are equal to L of s. And the second one, w be any one of the subspace means L of s contained are equal to w. L of s means that is the linear, when the linear span must contains given in the subspace, then automatically s is also a subset of subspace. Conversely, s contained are equal to w, or given the subset of the vector is x, x is also contained are equal to L of s. Because to write the linear combination of the vector x equal to summation, enter this part can also be written as sigma ai xi. I varies from 1 to n. Summation symbol is sigma. Okay, student, this one sigma can also be written as, that is the summation of the part. Sigma can also be written as this one. So summation ai xi, or I varies from 1 to n values, or that vector is an one vector is an equivalent to x equal to a1 x1 plus a2 x2 plus so on an xn. So all the xi elements are given in the subset. All the scalar elements given the treated as field elements. Okay. So finally L of s, because x being xi values given in the subset, and that subset must contains or contained or equal to w. So finally L of s, because that vector is consisting given the subset, so to write as can be written as a linear span of this part. L of s contained are equal to w. So s contained are equal to L of s, or L of s contained are equal to s. So a contained are equal to b, or b contained are equal to a. Finally L of s equal to yes. That is the third condition. Okay, because here L of s is a subspace of V. So finally, when the linear span is a subspace, linear of linear s. So to write as the linear of L of s equals to yes is there. That is the third condition we can prove. Okay, replacing of that value given in the fourth condition, L of s. So L of S equal to L of S. Finally, we are getting the value is the above the condition, third condition. See this condition, see and refer this one, third condition, that is an equivalent to capital S. Now the fifth condition, S contained are equal to T, or S contained are equal to T means one of the subset. That subset is to write as the linear combination, the linear span L of T. So L of S contained are equal to L of T by the second condition. Now that is the simple proof of this linear. From the above, we have discussed the linear span and their properties. So see this one, worked out exercise 1.4.1. This is one of the important theorem in the final examination. Don't forget this one. Now this theorem is also to be referred in the previous concept, previous class, just like that use the fourth semester algebra paper. The union of any two subgroups is a subgroup if and only if one is contained in the other. Actually, union of the subgroup, any two in union of the subgroups need not be a subgroup. Now, in the same manner, the union of any two subrings need not be a subring. Now, in the linear space of this part also, it follows that the union of any two subspaces need not be a subspace. But if it is a subspace, the union of the subspace, if it is a subspace, one is contained or equal to second one. So one is contained or equal to second one means first subspace contained or equal to W2 or W2 contained or equal to W1. So that is the when the union of the subspace is a subspace, that is the necessary part, and the sufficient part we must prove that one is contained or equal to another one. Okay. Now this is the simple proof. First of all, you have to take in. Please stay on the line. Please stay on the line. Please stay on the line. Up to 120. Okay. This class is also up to 120. Please remember this one, because we have to connect from the university. That is the late commencement of this class. So the union of the any two subspace is a subspace if and only if is contained in the other one. Okay. Hello. Hello. Please respond to the student.
Sir.
Okay. Amma, your name is?
Harita.
Harita. Okay, Harita garu. Now this class is also up to 120 because late commencement of this class. Okay.
Okay, sir.
Okay. Are you follow here? Any doubt?
Oh, yes, sir.
Okay. That's all right. Now, this is also one of the important theorem in the university examination, because now W1, W2 be any two subspaces of a vector space capital V over a field capital F, the union of the subspace if and only if one is contained in the other one. That is the theorem. Okay, this is the subspace of the algebra of subspaces. This theorem is also represented as algebra of subspaces, especially that is the union of this part. Okay. Now, just you have to see proof here. W1 contained are equal to W2 or W2 contained are equal to W1. First of all, so you have to take in this one. Now, then we must prove that the union of the subspace means W1 union W2. We are taking the any two subspace here. W1 comma W2 be any two subspaces. Then their union is also an equivalent to either W2 or W1 respectively, because the union of the subspace represented as W1 union W2. It is also a subspace of V. Conversely, suppose that the union of the subspace W1 union W2 is a subspace. Suppose W1 is not properly contained or equal to W2, or then we shall prove that W2 contained or equal to W1. Okay. choose X being the W1 or X is not in W2. X is in W1, but not X is not in W2. If this is possible, since W1 not contained or equal to W2 means here Y be any one of the element, because suppose W1 be any one of the element, that element is not in W2. But here, especially X is not in W2, but X is in W1. Okay. At the same time, Y is also belongs to, because that is the condition of here W2 contained or equals to W1. Okay. Because any union, suppose we are taking the one of the subset is capital A. Already some problems are practiced in the lower session. A equals to 1, 2, 3, B equals to 4, 5, A union B equals to 1, 2, 3, 4, 5. Because some B is one of the subset, one of the set. Here, that set not that set of the elements is not in A. All A is not in the given the B. A is also belongs to capital A is also consisting W1, B is consisting W2. So W1 not contained in W2, W2 not contained in W1. So that's why we are treating as the some base elements X is in W1, but X is not in W2, but X is also belongs to W1 union W2. At the same time, Y is in W2, but Y is not in W1. So that's why W2 is not, W1 is not contained or equal to W2. So Y is also belongs to W1 union W2. Union means overall the elements. Okay. So that's why here X and Y both elements are belongs to W1 union W2. So here the condition is X minus Y. Okay. Now here X minus Y is also belongs to W1 union W2. So that X minus Y belongs to W1 or X minus Y belongs to W2. Union represented as the statement of the symbol. That is the conjunction of this part, disjunction of this part. Union represented as the OR. Okay. X minus Y belongs to, this is the meaning of the union of this part means either X minus Y W1 or X minus Y W2. Okay. So X minus Y, suppose we are taking the X minus Y belongs to W2 is there. Now that is the contradiction of this part, because X is not in W2. Finally, X minus Y is not in W1 or X minus Y is belongs to, and hence this is the contradiction of this part means X minus Y is consisting W1. So Y can also be written as, Y element can also be written as X minus of X minus Y is also consisting W1 is there. Okay. Now Y is consisting is W2 means Y is consisting W1. So it is properly W2, same element is also contained or equal to W1 is there. So that's why we have proved that W2 contained or equals to W1 is there. Now this is the theorem of the union of any two subspaces is a subspace if and only if one is contained in the other. Now this is the simple proof of this problem or property, whatever it is. 1.4.1. This is also one of the important theorem in the final examination. Okay, that is the practice practice theorem in the above this part. This is the solution for you. Okay. Now see this one 1.4.2. The sum of the subspaces represented as W. What is the sum of the subspaces? Sum of the subspaces means that is the representation of W1 plus W2. Plus means that is the addition. So W1 plus W2 means sum of the subspaces is also a subspace. So W can also be written as W1 plus W2. Now here X1 be any one of the element, that element is consisting W1, and X2 is the belongs to W2. Sum of the element is denoted by through the sum of the subspaces means W1 plus W2 is also a subspace. Now that is simply notated as W equal to sum of the subspaces means W1 plus W2 equals to set of this is X1 plus X2. X1 belongs W1 and X2 is also consisting. It read as X2 is consisting or X2 is in, X2 belongs to whatever it is. So X2 is also belongs to W2. So sum of the subspaces is also a subspace. Now this is the concept for you. W equal to, W means sum of the subspaces. W1 plus W2 equal to linear span of the union of the subspace. The linear of union of the subspaces. Sum of the subspaces. Okay, we must prove that sum of the subspaces is an equivalent to the sum of the subspaces of their linearity or linear span of some of the subspaces. Okay, so this is also one of the important here. W means W1 plus W2 equals to linear span of the union of the subspace. Now this is also a simple proof of through then their understanding of the part of the above definitions, linear span and union of the subspace. First of all, so you must write the linear span L of S or and at the same time union of the subspace W1 plus W2 is an equivalent to W2 equal to set of X1 plus X2 such that here X1 belongs to W1 and X2 belongs to W2. Okay, students, listen carefully. Now the linear span means here that is one of the any non-empty subset S of V is also a subspace of V. Already we have derived here. Now it is enough prove that sum of the subspace equal to linear of union of the subspace, means that is the linear span from union of the subspace. Here X be any one of the element sum of the subspace. So here X belongs to W. So that's why X can also be written as X1 plus X2. Here X1 belongs W1 and X2 belongs W2. See this one. See this one. Okay. Now this is X1 comma X2 is also belongs to W1 union W2. Okay. Now here X is also consisting, that element must be generated. Generated means that is the span. So that is L of W1 union W2. So X be the element of W. So that's why W contained are equal to L of W1 union W2. So that can also be written as X1 plus 1 Xn plus Y be the element union. Second subspace of the element is Y. We are taking the elements is Y1 plus 1 Ym. So entire the linear span can also be written as the linear combination of the vector given the linear span of union of the subspace. So that's why here X1 plus so on plus Xn plus Y1 plus so on plus Yn. All the X element is consisting W1 and all the Y elements are consisting W2. That's why all the Xi elements is W1 and Yi elements, some of the Yi elements, that is the linear combination is W2. So finally, linear of the subspace, it is of the form Z1 plus Z2 because X1 plus Y1, X2 plus Y2, so on Xn plus Ym. Okay. So that's why here X1 plus Y1 means Z1, X2 plus Y2 means Z2. So that's why we are taking the form X elements are denoted by Z1 and Y elements is denoted by Z2. So finally, the union of the linear span, Z1 is consisting W1, Z2 is consisting W2. Finally, W equals to means sum of the subspaces is an equivalent to the L of W1 union W2. See this one. Okay. Now the entire that value is contained are equal to W. So finally, A subset are equal to B, B subset are equal to A. Finally, A equals to B is there. So students, this is also one of the important 1.4.3. The intersection of any two subspace equal to generated by 0. See this one. That is a simple expression. Sum of the subspaces is denoted by V. So that vector space is an equivalent to W1 plus W2. So W1 and W2 both are subspaces of a vector space. This is 1.4.3. The sometimes are also given in the one essay question and one short answer question is given. In that behalf of the time, continuing of the each and every one is important. Enter all the theorems and problems must connected or connecting with the further session. Okay. Now that is the uniquely expressed is of the form X1 plus X2. Here X1 is belongs to W1 and X2 belongs to W2. Okay. Now here sum of the intersection of any two subspaces is an equivalent to, okay, sum of the linear sum uniquely expressed as intersection of the subspace equal to generated by 0. So that is denoted by W1 intersection W2 equal to generated 0. This is the concept. Now then their answer is here. See this one. First of all, we must take in the any one of the element given in the uniquely representation. X can also be written as sum of the subspaces. Means there are two subspaces x1 plus x2. Because any vector x is belongs to V and x1 belongs W1, x2 belongs W2. So that's why the intersection of the subspace is 0 be any one of the element of the intersection of the subspace. So that intersection of the subspace is non-empty because at least one element is here. Okay. Now 0 can x can also be written as what is the additive identity? X can also be written as adding with 0, x plus 0 or 0 plus x, because 0 and x both are belongs to 0 is also, first of all, this is taken 0 plus x, 0 belongs W1 and x belongs W2. Suppose x plus 0, x belongs W1 and 0 belongs W2. So there is no problem here, and uniqueness of this concept, if suppose x equal to 0 means the intersection of the subspace is generated by 0. Conversely, that is here taken intersection of the subspace equal to generated 0. So sum of the subspaces represented as given the vector space V equal to W1 plus W2. Now in the irrespective of the elements, x equal to x1 plus x2. Here x belongs to V and x1 belongs W1 and x2 belongs W2. That is the uniquely representation of the form linear combination. So x1 plus 2 uniqueness means to write as the in terms of x and to write as the in terms of y. Now both are sum of the vectors, both are it is an equivalent. So now both values are x1 equal to y1 and x2 equal to y2. So because here x1 y1 belongs W1 and x2 y2 belongs W2. So here x1 minus y1, this can also be written as x1 minus y1 equal to y2 minus x2. So x1 minus y1 means the intersection of the subspace is equal to generated 0. Suppose either x1 minus y1 equal to 0 and at the same time y2 minus x2 equal to 0. So finally the both all the elements are equal, x1 equal to y1 according to this condition, and according to this condition x2 equal to y2. Okay students, now this is the concept of this one. Now in the same manner, just you have to see and refer 1.4.4. okay, now that's enough, this is not necessary. And at the same time 1.4.6, the union of any two subspaces of the linear. So linear of the subspaces equal can also be written as L of S plus L of T. This is also one of the important in the final examination. Define linear span in the examination point of view, because this question is given, define linear span and prove that here S and T both are subsets of a vector space. L of S union T equal to L of S plus L of T. This is one of the important theorem in the final examination. Okay, 1.4.6. Now this is the end of this unit. In the especially first of all, so you must practice in the final session, especially in the first unit, very most important in the further session. Okay. Now that is the second part of this concept. That is the basis and the dimension. This is one of the important concept, because further theorems and further those theorems are depends upon the basis of a vector space and the dimensional of a vector space. There are number of theorems throughout the basis and the dimensions. And already before the concept, before that topic or before that unit, what is the unit? That is the vector space and the subspaces. Linear span. Now that is the end of this unit. Linear span and those the properties depends upon the linear span. Okay. Now through the linear span or linear combination of vectors, what is the linear dependence and independence? Now one of the most important concept, dependence and independence. Okay students, already time is over. Tomorrow we will discuss the next class. We will meet again the next class through this concept, linear dependence and independence. Now the remaining classes are 4 classes are remaining here. Some important theorems and important problems we will discuss in the further session. There is no doubt. If you have any doubt, please contact my number. That please note down my number 9989476833. This is my number. And if you have any doubt, you must contact us and personally through WhatsApp. We will discuss the subject point of view. There is no doubt. Thank you one and all. And once again, if you have any doubt, please contact us and personally my number, because more class, some less classes are here. Remaining classes are just like that. 4 classes are remaining here. Okay. Especially last 2 classes, we have discussed the characteristic roots and characteristic vectors and Cayley-Hamilton theorem. That is the last 2 classes. And at the same time, and some problems are practiced based on Cayley-Hamilton theorem, because that is one of the important theorem in this, especially in this 5th semester examinations. Okay. And last class we will discuss the inner product space. That inner product space, some other inequalities, the definition of inner product space, and at the same time both that inner product space definition is also depends upon the linear space. Why? Because we have practice thoroughly from the basement, from the bottom level. Okay, that is the basement of this part, because this is the linear space, and through the linear space definition to practice and some other examples depends upon the further session. Okay. Now, thank you one and all. Once again, wish you all the best and wish you good luck.
Thank
Hello?
you, sir.
Okay. Any doubt?
No, sir.
Okay. Okay, Nama. Wish you all the best and wish you good luck. Please,
Thank
please inform this, especially this meeting ID and password. Your friends also discussed here. Okay, because previous ID is not connected in the university part. Okay.
Okay, sir.
Please inform each and everyone. Thank you once again. Wish you all the best and wish you good luck.
Okay, sir.